Hello and welcome back. This is Computer Science 2, CSCE 156 and 156H. And today we're starting on our last major module, which is trees and tree-based data structures. And I thought I'd do something a little bit different here today. I've got the overhead projector set up for handwritten notes as usual, but I'm also going to be providing notes on the right-hand side here that are eventually going to be committed to GitHub along with everything else. Remember that we do have a live Q&A set up with Piazza, so if you've got questions throughout, make sure that you go ahead and post on Piazza about it. Okay? But otherwise, we're going to be looking at today. First, we're going to be introducing the notion of trees and how to use trees as data structures. Basically, our motivation is going to be to try to put more and more structure into our data structures that we can then exploit for efficient operations. The motivation here is that it's really a quest for an ultra efficient data structure that can hold elements and provides a efficient retrieval or search of elements, the insertion of elements, and the deletion of elements. So basically, the basic CRUD like we cover with databases. We want to be able to create, retrieve, update, and destroy elements from our data structure. Now we've already looked at a couple of data structures here. One data structure is lists. In fact, we looked at two versions of lists. That we looked at linked lists, right? And does this fit our definition of, or does this fit our quest, basically? Well, it does offer constant, that order one is, remember, constant, time operations for insertion retrieval, and deletion from the front and back. That's the head and the tail. Right, let me go ahead and use head and tail. Right. So you can do those operations, but it's a kind of like a restricted access data structure, which makes it perfect to use in a queue or a stack kind of situation where you want to implement those things. And those are going to be order one. In other words, they're constant time operations. However, it's going to be order n for most other arbitrary operations. If you want to have an index-based retrieval method, or an index-based delete method, or an index-based add method, then you'd have to traverse the entire list to get to that index in order to insert or update that element. So linked lists do give us partial, but not everything. Array-based lists have the similar problems, right? They're if sorted, then we have an order log n search or retrieval, or search feature, right? But of course, it has to be sorted. We achieve that through binary search. If it's sorted and it's array based, then that means that we can exploit the structure of the array. And we can exploit the random access of the array to jump to the middle to search what we're looking for. And we can also exploit the structure provided by the fact that it's sorted. Even if it's unsorted, you still have efficient, that is order one, index-based retrieval, right? However, it's going to be order n for insertion or deletion. Remember, the reason for that is you've got to make room for it. So if you want to insert something at the beginning, unlike a linked list, you have to make room for it, and so you have to shift n elements down if there are n elements in there already. Each implementation of list has its use cases, has its applications where you would actually want to use it, and they're a little bit different. But what we want is, ultimately, we want efficient operations for all three of these things. Okay. Now the holy grail for that is going to be, of course, a hash table or a hash-based data structure. But that's not what we're covering here. What we're going to look at is trees, right? So alternative is potentially trees, right? Trees. we're going to use those as our data structures. They basically have the potential to offer order log n operations for all three operations, right? Complexity for all three operations, okay? And that's why we're going to be looking at them, because they provide efficiency on all three of those aspects, not just for binary search. Although the reason that we're looking at trees is because it's going to look very similar to binary search in that you look at the middle element, and then that effectively splits the number of elements in half, and then you can iteratively or recursively descend down the tree and find what you're looking for. Okay. Before we get there, though, we have to introduce some basic notation and some basic definitions. So, introduction to trees. Okay. So first of all, a tree is a graph. What is a graph? Well, a graph is simply it's not like a graph where you would graph the x-axis and the y-axis. What we're talking about here are vertices. Each one of these points is a vertex, and edges. Edges can connect vertices, right? I'll go ahead and connect it like this, right? There's a basic graph where you have vertices and edges connecting them. Now, general graphs are very, very useful. In fact, you've seen them and you've used them up to this point in multiple scenarios. When you generated an ER diagram, an entity relation diagram for your databases, that was a graph. The vertices were represented by tables, and the relationships between the tables were represented by those by arrows, or by the chicken foot kind of one-to-many relationship. You've also hopefully seen them and maybe are using them with respect to your class designs, because a UML diagram, a universal modeling language diagram, has classes as the vertices, and then relationships between them are represented through various arrows. Right? It turns out that graphs have a huge number of applications. Basically, any relationship that you can come up with, you can model using a graph. And there's a whole litany of graph algorithms, graph results, and things that tell you about how various toolkits that you can use to run analysis on a graph representation of a real world problem, and then that gives you an answer to some sort of question with that real world problem. If you model it using a graph, then it opens you up to using this entire toolbox. Okay, but unfortunately, general graphs don't have a lot of structure that we can exploit. A lot of common problems on general graphs become very, very difficult and have exponential time algorithms that are required to actually solve those problems. So what we want to do is we want to put a restriction on our graphs. The way that I drew this is I've got what's called a cycle here. So if I start at this vertex and then go to that vertex and then go to that vertex and go to that vertex and then repeat and come back over here, that forms what's called a cycle. Okay. Now, of course, if there's no edge between two vertices, then that just means that you can't go directly from that vertex to this vertex. There is what's called a path from that vertex to this vertex by following here, here, and here, and that's a path of length 3. We'll get to those definitions here in a second. But this is a cycle. Right? Cycles can cause a lot of problems because you can get caught in a cycle. So what a tree is a tree is an acyclic graph, right? That is a graph with no cycles. So this is not a tree right here. To make this a tree, I would have to delete at least one of these at least a couple of these edges, in order to make it a tree, in order to take away all the possible cycles. In fact, there are 2 cycles here. There's one cycle there, there's one cycle there, and then of course there's the large cycle out of this. And then you can have any number of combinations of cycles here. So that's not what we want. We want more structure. We want a restriction on our structure in order to exploit that structure so that we can have some efficiency. Okay. For our purposes, we don't generally call them vertices in this context. For our purposes, a tree is a collection of nodes. Instead of vertices, we call them nodes. Vertice, because it's just a small point of technicality. Nodes generally hold data. So vertices that hold data or something, right? Or represent something. ER diagram, they represent a table. UML diagram, they represent a class, right? So we usually call them nodes that are connected by edges, right? And in this case, they're undirected. There is no orientation. Right? Now you can have graphs that have directed edges, right? If I've got A here and an arrow in my edge, A goes to B. That is an oriented edge. I'm going from A to B, and likewise, I can't go from B to A unless I've got what's called a back edge that goes both directions. That's what we're going to consider. Directed graphs are very important, and you might have seen them, and you might you'll definitely encounter them later. But what we're looking at right now is an unoriented edge. What that means is if you start at A, you can go to B. If you start at B, you can go to A. It's basically I have both of these edges over here, and I just collapse them and take away the orientation. Right. So these are undirected edges. Okay. In addition, for our purposes, a tree can be oriented, right? So what I'm going to do is I'll reuse this paper. I don't want to waste too much paper here, even though it's going to end up showing through here. All right. So let me go ahead and draw a tree, and for our purposes, our data is simply just going to be letters for now. But of course, you can imagine that you would store an instance of a student or an instance of some class here or something like that. All right. So here is a tree. Let me go ahead and draw a few more here. There we go. And there. Now, if I draw any more edges here, then that means that I'm going to have a cycle. And that's not going to be a tree. You can observe here that everything is connected. You could have, let me go ahead and draw one more edge, vertex here, or one more node. And you could have a disconnected component here, GH, there we go. All right. And that you can have a collection of trees. That's called a forest, right? We're not that creative here. We're just reusing terminology from that we've got multiple trees here. Right. This is an acyclic graph. This is an acyclic graph. If you take the union of them together, they are disconnected here. That from H, I can't get to any other component over here. And so this is a connected component. This is a connected component. But overall, the graph is disconnected. All right. We're not going to consider disconnected graphs. We're not going to consider forests. We're going to restrict our attention to trees. But you can see that you can have multiple components here. Now, if I draw any more, I'm going to go ahead and draw this one edge right here. If I draw any more edges here, that will automatically induce a cycle. If I drew an edge right here, that would be a cycle here. If I drew an edge here, that would be a cycle here, etc. Right? Now, this is a tree. It's unoriented because, you know, even though as humans, we tend to want to organize things. And so you saw me drawing them in kind of rows. I was trying to get away from that. You can have just some random tree drawing here. But what we want to do is we want to organize this tree. Now, the way that you can do that, take any tree, take the node, and imagine me pulling it out of the paper and then using gravity to dangle it all so that all the nodes fall down, even though they're still connected, and they all fall down. If I did that off of B, what might that look like? B would be at the top, right? I'm dangling it now from this piece of paper. B is connected to A, D, and F. So I could write that as A, D, and F. And don't lose the forest for the trees. Don't lose the don't lose your connectivity here. Well, if I did that, then the E, which is hanging off of A here, would then dangle below it because of gravity, right? If I looked at D here, it's connected to C, so it would hang down off of D. Now F has a bunch of other things connected, and it would all end up, falling down because of gravity. And I've got G and H. Right? That's one way of doing it, right? But it's an oriented way. Another way of doing it, if I grabbed, I don't know, arbitrarily here, if I just grabbed F and lifted it out of my paper and started dangling it, it would look a little bit different. It would have F up here at the top. Off of that, it would have B and G. G would have H hanging off of it still. And then it would look very similar to this over here. B is connected to A and D, but F is already up here. So it would be A and D. And then off of A, we have E. And off of D, we have C. So it looks a little bit different. It's the same graph. These two, all three of these things are the same exact graph. All three of these things are the same exact tree. But now these are oriented. Right? This is the top of the tree, and this is the bottom. Right? And we can start to use some terminology here. Right? At the top of the tree is a single node called the root. Right? So in this case, B is the root, F is the root. Okay? At the bottom of the tree are leaves. Right? So in this case, let me just go ahead and restrict it over here. H, E, and C are all leaves. Right? So I'll use a different color here. These are leaves, and this is the root. Right? Now, normally trees grow upward, right? And we've got the roots down at the bottom, and then they grow up, and the leaves are at the top of the tree. Don't ask me why, but 150 years ago, I think it was due to Cayley, a mathematician named Cayley, who first established the use of trees for in mathematics. His original paper 150 some years ago also had them growing down. And the reason being is that this is ultimately going to hold data. And as humans, at least as English speakers, most of us, are going to read data top to bottom, left to right. So we want to start our tree at the top with the root. So it's just something that you have to get used to. We do this all the time with other kinds of trees, like family trees. Family trees also grow down. So it's just something that you have to get used to. Right? Otherwise, a node that is neither a root nor a leaf is an internal node. Right? So, for example, B and G are internal nodes. Right? And we can also orient this further. Each node may have a parent and or children. Right? So, like I mentioned, we've got family trees growing downward. We use the same naming conventions here, right? That we've got, and let me go ahead and do another diagram here in general. If I've got a node U, right, then we can look at its parent. This is the parent of that node, and unfortunately here we don't. We're only going to ever only have one parent, because if we have another parent over here, like in a family tree, remember the orientation. I was dangling it. That parent would come down here and actually become a child. All right, but we have children down here. We could have a bunch of nodes down here. Okay. Now you can use other terminology. You can use ancestors, and not the immediate children, but more nodes down here. You can call those their descendants. Right? So each node may have a parent, and each node and or children, and you can also use ancestors and descendant terminology. And you can also bring in cousins, aunts, uncles, grandchildren's grandparents, right? You can bring all those things in, and it makes sense in this context because it is an oriented tree that's oriented downward, okay? All right. Well, that's not enough. We want another restriction here. A binary tree is a tree such that is an oriented tree, I'll say, is an oriented tree such that every node has at most 2 children. Right? That's where the binary comes in. Binary 2, at most 2 children. Of course, it could still have a parent. It could have no children, right? A leaf. And it could have 1 child or no child, or 2 children, right? Not only that, but we're going to orient them. Orientation can also be done horizontally. Right? We can have a notion of a right child and a left child. Right? So again, let me go ahead and take this diagram here, and let's look at it from a different perspective. If we have this restriction, then we have at most 2 children. We have a node U, potentially its parent, and its left child, L, and its right child, R. The left and right is from our orientation when we're reading it, and this is the left side, this is the right side, okay? And of course you've got, again, ancestors and descendants, grandchildren, whatever you want here, all right? So this is a left child and this is a right child, okay? All right, checking in with Piazza, no questions so far, so I'll continue. Some additional terminology then, right? Additional terminology. A path in a tree is a sequence of edges connecting nodes. Okay? So for this, let me go ahead and actually draw a full binary tree at this point. And again, I'm not that creative, so I'm just going to pull one that I have from the textbook here. Maybe not as big, since I don't want to redraw everything. And again, since I'm not being all that creative, and again, because trees hold data, we tend to read them top to bottom, left to right. So I'm going to be labeling these nodes A, B, C, D, E, F, G in order, top to bottom, left to right. Actually, maybe I will go ahead and copy this one entirely. And I'll reuse it. I'll try not to mess up the diagram too much with a permanent marker. Instead, I'll switch over to a pencil if I can. F, or right off to the side here. J and K. Right. So as I'm doing this, you'll observe that the root is A. Excuse me. A has both children present. If it had a third child here, it would not be a binary tree. It would have, you could have a ternary tree, quaternary tree, and you can talk about things like that. Some of these nodes have both children, just like A does. J has both a left child and a right child. K has no children at all, and so it makes it into a leaf. Right? O here has no children at all. Let me go ahead and continue drawing more on the tree here. The G and H. H has a right child. There we go. It's called. I'll call it N. And let's see, L and M. I really should have just used it from the book because I don't know if my drawing is all that great here. All right. So some things have no children, which are all leaves down here at the bottom. Some things have a left child but no right child. Some things have a right child but no left child. And other nodes have both children present. Okay, so I've got a whole variety here. Okay, now let's make some observations. The first observation that I want to make is that the root is A. How many leaves are there? There's L, R, N, O, P, and Q, and K. These are all leaves. Otherwise, everything else is an internal node. Okay. Consider the following paths. There is a path from, say, A to O. A goes to B, goes to E, goes to I, goes to O, right? Now, what's the length of this path? Well, it has 1, 2, 3, 4, 5 nodes on it, 5 nodes on the path, and 4 edges connecting them. Right? In fact, on any path, if you have n nodes, you're going to have n minus 1 edges between them, because if you've got 5 fingers, if you've got 5 fingers, you've got 1, 2, 3, 4, 4 gaps to connect them all. Okay. So for anything, if you have a path with n nodes, you have a path with n minus 1 edges. Right? And the length of the path, the length of a path, is the number of edges on it. Right? We only consider simple paths. So what you can do is you can go over here and say, okay, well, I can go from A to G by going from A to B, then taking a little detour here and going over to E, I, O, and then coming back, backtracking, and going all the way over to E. That's not a simple path. A simple path only traverses a path that only traverses an edge or a node at most once, right? So you can't take this detour down here because it would require you visiting E twice. Once when you're going down and then once when you're coming back up, okay? We only consider simple paths or simple cycles if you do have a cycle, but again, we're focusing on trees here, so we don't have any cycles, okay? All right. Well, because it's oriented, we've got some additional terminology that we can look at. The depth of a node is the length of the path from the root to it, of a node U. I'll give it a name, to U, right? So, for example, what is... try to reuse as much as I can over here. What is the depth of J? Well, if I start at the root and go 1, 2, 3, then the depth of J is going to be 3. Right? What about P? The depth of P is 1, 2, 3, 4. That's how long, that's the depth of the node there. Now, there are paths that are longer. For example, I can start at G to get to K. I have to go all the way up to the root and then traverse back down this tree. So that's 1, 2, 3, 4, 5, 6. That's a path of length 6. But the depth of a node is once you've oriented it, then you've got a root up here. The depth is simply going to be the length of the path from that root to any other node here. Right? Well, what about the depth of B? Well, the depth of B is just 1. Then you can also ask yourself, well, what's the depth of the root itself? The root's depth is always going to be 0, because what is the length of the path from A to itself? Well, you're already there. You're not going anywhere. You're not moving. So it's a path of length 0. Right? What about R? To get there, I would go 1, 2, 3, 4, 5. That is actually the deepest node. So consequently, the depth of a tree of itself, the depth of a tree itself is the maximal length depth of any, or I should just say maximal depth of any node in the tree. Right? So for example, an empty tree. The depth of this tree here, it's going to be 5 because there's no other node deeper here, and that's why I drew it like this. In fact, you can actually call these levels. This is level 0 or level 1. You could alter that and be off by 1 here if you want to. This is the second level, or level 1. This is the third level, or level 2, right? And so the thing at the deepest level, that is going to be the depth of the tree itself, right? What about some special edge cases here? For example, here's another smaller tree, A, B, and C. What's the depth of this tree? Well, it's just 1, because the deepest nodes here is B and C. They have the same thing. That's why I say maximal, because there's not guaranteed to be a maximum. It's not guaranteed to be unique. So the depth here is just 1. Well, what if I had A and B? It has a left child but no right child. Same thing here. The depth here is 1 of this tree. What if I had just a single node tree? Right? One year somebody suggested that we call these seeds, and I really like that terminology. So I think I put it in the book, but I don't know who to give credit there for, who to give credit to there. So what's the depth here? Well, the maximum depth of any node, there's only one node, its depth is 0. So the depth of a single node tree is going to be 0. You might also ask yourself, what about the empty tree? Right? Empty tree. And you can have empty trees, just like you can have a graph with no vertices, the empty graph. By convention here, the depth is going to be -1. Right? Just because if you make it small, if you start trimming the tree out, start cutting things off, you start pruning the tree, now your depth is smaller, and if you prune it all the way out, now you don't have a tree at all anymore. You've cut everything down, and it's just following this logical conclusion of, you go from 1 to 0. Well, the only place you can go now is -1. Okay. All right, so the depth of a tree itself is the maximal depth of any node. A single node tree, we'll call that a seed, has depth 1, right? An empty tree, these are just some corner cases here, has depth -1 by convention, right? It doesn't actually make sense to talk of negative depth, just like it doesn't make sense to talk about a negatively sized array, but for convention, to make some mathematics work out, we do use that convention. Okay. So now some observations. Because a tree is acyclic, there is and connected. And here I'll switch over to binary tree here. Because a binary tree is acyclic and connected, there is exactly one path between any two nodes, right? And consequently, there is exactly one path from the root to any node, period. Right? That's the structure that we're going to exploit. Because with just a general graph, there can be an exponential number of paths going from A to B. You could traverse an exponential number of paths backwards and forwards. Non-simple paths, if you throw those in there, they're now infinite, because what you've got, if there's any cycle, you can go from A, jump into the cycle and go around it as many times as you want, jump out of it, and then go to B. So we've really simplified the situation here. Because of this, because we've made it acyclic, because we've made it connected, and because we've made it simple, we've given this our tree structure more structure. That structure is something that we can then exploit. For if we're storing data in this stuff, then we're guaranteed that if we start at the root and go to any other thing, there is exactly one path, there is exactly one way of doing it. And if there's only one way of doing it, then that really simplifies the situation. Okay? We have we have even more structure. Right? At any depth, there is a very predictable maximum number of nodes. Okay? At any depth. Okay? What I want to do now is I want to actually I'm going to save this because I want to reuse it. But what I want to do is I want to look at what's called a full binary tree. Okay? So to see this, consider consider a full binary tree of depth D. Right. What I mean by full is that every node is present, every child is present except for at the last level. Okay, so I'm not going to label them here, but I am going to draw them. And this is going to be complex very, very quickly here. I'll only go down a little bit, but we will keep track here. Let's go ahead and write out what the depth here is. Depth, or if you want to, level. Right? The depth here is 0. The depth here is 1. The depth here is 2. The depth here is 3, dot, dot, dot. If I continued on and I had a general depth of the tree being D, okay? How many nodes are at every level? So the maximum number of nodes, or in this case, since it's full, it's going to hit that maximum. At depth 0, we only have 1. That's the root. At depth 2, you can see that it's doubled now. In fact, you can see that pattern that it's going to double at every depth as we go down. 4, here, you can count them up yourself, but they're going to be 8, dot, dot, dot. And at depth D, you can see the pattern here. There's going to be 2 to the D nodes. Right? Now what I want to do is I want to sum these all up. Okay, what's the total sum? The summation of I running from, by the way, this starts at 2 to the 0. So we'll start I at 0 here, up to D of 2 to the I. We're summing powers of 2, so this is a series. Right? This is going to be 1 plus 2 plus 4 plus 8, dot, 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 all the way up to 2 to the D here. Now, hopefully you remember this from algebra or calc or wherever it's covered. But if you don't, that's fine. I'm going to tell you what it is. It's 2 to the D plus 1 minus 1. Now, let's just verify that here. What if I cut my depth off here at 3? There are going to be 1 plus 2 plus 4 plus 8. In total, that's 15 nodes. Now, the depth here would be 3, so it is 2 to the 3 plus 1 minus 1. Well, that's 2 to the 4, which is 16, minus 1. That gives me 15. Right? That's the general formula right there. So if I have a full binary tree where every node is present at every level up until the last level, D, then I have, at the last level here, I have 2 to the D leaves. Then what if I looked at it from the opposite direction? In other words, what if I started, suppose you have n elements to store in a tree. What is its depth if full? We actually cannot guarantee that a tree is going to be full. The example that I gave you initially, that's definitely not a full binary tree. There are entire branches here that are missing. If this were full, I would end up drawing many, many more. In fact, how many more? 1, 2, 3, 4, 5. This is a depth 5 tree. So for a depth 5 tree, for D being 5, that's going to be 2 to the 6th minus 1. 16, that's 64, that's 63 things, and I'm not going to be drawing all of those, okay? But the point that I want to get across here is, if it's full, then what's its depth? I'm going to take this and suppose that I have n elements. N elements, that's what I start with. And if it's full, then it's roughly going to be 2 to the D plus 1 minus 1. Now, to answer the question of what's its depth, all I need to do is solve for D. So I will take 1 onto the other side. N plus 1 is equal to 2 to the D plus 1. To get rid of the, I need to solve for D. So to get rid of this 2, I'm going to take the log base 2 on the left hand on both sides. Log base 2 of N plus 1 is equal to D plus 1. Right? And then I'll take the 1 on the other side, and I'll end up with D is equal to log base 2 of N plus 1 minus 1. Now, you don't have to go through a full formal proof here to see that this is going to be, that if it's full, then the depth here is going to be order log n. Right? So why is that good? Right? So for a full binary tree with n elements, we'll have depth d being order log n. It sounds very familiar, right? If with binary search, we were able to do our operations in order log time, right? That represents an exponential speed up of linear search. Maybe the whole point here is if, and that's a big if we can establish the basic operations, that is insert, update, delete, etc., and they are proportional to the depth of a tree, then we've achieved our goal. We've achieved an order log n complexity for all operations. Right. Now, achieved, there we go, for all operations. That was our quest at the beginning. Right? If we can achieve that, then we will have achieved our goal here of having a very nice data structure that offers logarithmic, huge speed ups, exponential speed ups over both an array-based list and a linked list, and everything ends up being logarithmic. That is a big if. In fact, we will not get to that as a guarantee because, as we've already seen with this example, there's no guarantee that a tree has to be full. There's no guarantee that a tree has to be, proportional. In fact, we can have degenerate trees. Consider the following tree with 1, 2, 3, 4, 5 elements in it. What's its depth? It's 4. That should look very familiar right there. If I just turn it around here, that's a linked list. A linked list is a degenerate binary tree, such that now instead of having at most 2 children, you have at most 1 child, right? And so you can have situations where a binary tree devolves into just a regular old linked list, but that's not what we want. Unfortunately, we're not going to be able to get to that guarantee. There are what are called balanced binary search trees. And if you take Computer Science 3, you'll cover those. Balanced binary search trees like AVL trees or 2-3 trees or red-black trees. There are at least a dozen different variations on balanced binary search trees. We haven't gotten to binary search yet, but binary trees that basically rebalance themselves. If they become too skewed to one end, then it rebalances so that they're basically balanced again, right? Balanced binary search trees. Okay? All right, let's see. But that ends our motivation there. What we need to do now is we need to build some tools and have a full arsenal of tools available to actually operate on trees. So basic tree traversals. Right. So with a linked list, a traversal is pretty straightforward. You start at the head of the list and you go to the next one, the next one, the next one. There's only one choice. You can either go forward. I guess there's 2 choices if you want to go forward or backwards, but your choices are really restricted here, right? And so if you want to search and you want to do an arbitrary search on a linked list, well, all you have to do is start at one end and just keep going forward, keep going forward, keep going forward until you find what you're looking for, or you get to the end. And there's really no guesswork there with a linked list at all. But with a binary tree, there are lots of options, right? If I start at the root, that's the natural place to start. Start at the top, work your way down. You could start at an arbitrary internal node if you want, but that doesn't make that much sense. You could start at an arbitrary leaf if you really wanted to. But the reason that we orient these things is so that we can read them top to bottom, left to right. So what I'm going to do is I'm going to, in general, start at the root. In general, you start at the root. Right? Our goal is to be able to enumerate or view or traverse every single node at most once without missing any. Right? So you could start up at the top here, but you have a choice now. Do I go that way or do I go that way? If I choose to go that way, to the left child, I need to make absolutely sure that eventually I come back to the right child and process it, right? Because I don't want to just explore half the tree. I want to be able to explore the entire tree. So I have to have a way of remembering that, oh, by the way, I'm going to go to this one, but by the way, I need to come back to that one eventually, right? I need a way of laying down breadcrumbs. Breadcrumbs that, if I'm just at an arbitrary internal node here, G, where did I come from? Did I come from the parent? Or did I come from the left child? Or did I come from the right child? How did I get here? I need breadcrumbs tracing all the way back up to the original up here. Okay. There are a couple of ways of doing this, and we'll be looking at each one of them in detail. But there's a pre-order traversal. Sometimes people hyphenate this. I think it's technically one word. There is an in-order traversal, and there is a post-order traversal. Right? So let's go ahead and focus on each one of these in turn. A pre-order traversal, recursively. Now, we're going to present it as recursively, but ultimately when we implement this, we're actually going to use iteration instead. But it recursively visits nodes in a left, right, root manner. Right? And I'll visualize what that means here in a moment. A post-order traversal and an in-order traversal and a post-order traversal, change this slightly. With an in-order traversal, you go left, and then you go root, and then you go right. And a post-order traversal actually does... oops, sorry. I screwed up here already. It goes pre-order traversal, the root comes first, left, then right. And then finally, the post-order traversal goes down to the left one first, then the right one, and then visits the root node. All right? So let me go ahead and visualize that over here. If I've got just a general node here, I came from potentially a parent. I've got a left child and a right child. So I came down to you with a pre-order traversal. What I do is I examine, or I traverse, or I process whatever data is in here. I process it, I examine it, I do whatever I'm going to do with this data. I do the root first. Then I go down to the left. Then when I'm done completely with the left subtree, there might be an entire tree hanging off of this. I explore the entire thing before I come back and explore the right tree. I do that after. An in-order traversal does it by going... I skip you. I came into you, but I'm not going to process it yet. What I'm going to do is I'm going to go down to the left subtree first, process that entire left subtree. Then I'm going to come back. Then I process you before going on to the right subtree. And again, doing the entire subtree over here. A post-order traversal does it by going to the left subtree first, coming back, ignoring you for now, and instead doing the right subtree first and everything in it. And then finally, at the end, once I've explored the left, once I've explored the right, I explore and process you. The only difference between these three is when you're doing the root, right? When you're doing the main node here, right? That's it's not the root of the tree, but it's the root of the subtree rooted at that particular node. Okay. Now you might ask yourself, well, wait a second. Oh, there's another possibility here. In fact, if you have U, L, and R, the number of permutations of those three things is 6. Where are the other 3? Well, the other 3 are just simply taking left and right and reversing them. So if you wanted to go right before you went left, be my guest, but then you're reading it in reverse. Why do that? In fact, I could take your tree, I could flip it around, right, and make the left child the right child the left child, and now we're back to square one with the going left first. So there's really no value in going right first over left first. We read left to right anyway. You might as well just stick with it. Okay? So to demonstrate this, let's actually look at this example. Since I want to reuse it. There we go. Let's do a full pre-order traversal. of this tree. Then we'll talk about implementation implementation details later on, maybe next week. A pre-order traversal means that you are doing the root first. So it's going to end up being A, process A. Then we go and do the left subtree before we come back and do the right subtree. So I'm going to come down. Now here's my world. Now I'm at B. So I process, B is the new root of this subtree. So I process it. And you can see that I'm going to continue going down in this fashion. D is the next one, then G, then L. At that point, I've got, my world here is now a seed. It's only a single node tree. There is no left child, there is no right child, so I'd end up not processing them. Now what I need to do is I need to come back to where I came from, G. This is where those breadcrumbs are going to come in. And the way that we're going to keep track of those breadcrumbs is either through recursion and abuse the call stack, or the way that I'm going to show you how to do it later on is to use a stack. Remember, a stack is used for, it can be used to determine where you came from, breadcrumbs, right? Just like I mentioned before, Hansel and Gretel, they were left breadcrumbs to go into the forest. We went from A to B to C. We went from A to B to D to G. That's how we got here. And then when we went to L, okay, well, my breadcrumbs tell me that if I'm done, then I need to go back up to where I came from, G. Okay? At that point, now I've enumerated G. I've taken care of its left subtree, so now I can take care of its right subtree. Its right subtree is M, and then I process its left node, which is R. Right? And at that point, I'm done. There is no right child to process, so I return, return, return. Right? Now at D, I've already processed D. I've already processed its entire left subtree, G, L, M, and R. So what I need to do now is take care of its right subtree. I go down to its right subtree. I process H. There is no left node to process, so I process its right node, N. This is H and N. And then I come back up and I return to where I was. I return again because I've done the node, its left subtree, and its right subtree. So now I'm at B. I've already done B. I've already done its entire left subtree, which covers D all the way up to N. And so I take care of its right subtree now. This is E. There is no left subtree to go to, so I go to the right subtree. That's I. That's the root. And then I go to its left subtree, O. There's no children there, so return. There's no right child, so return, return. And now I'm all the way back up to A. I go down to its right subtree, process the node, C. There is no left subtree, so I end up skipping it. I go down to its right subtree, process F. Left subtree, J, P. And I've already done J, I've already done its left child, and so I end up doing its right child, Q. Return, return. I've already done F. I've already done its left subtree, so I need to do its right subtree, K. There's no left child, there's no right child to K, so I return, return, return. And at that point, I know that I'm done because I've enumerated everything. I've enumerated everything in a pre-order traversal manner. Right? Let's do the same thing, but we'll do it in an in-order traversal. So in-order traversal. Again, one word. No questions on the live yet? Let me double check. Oops, sorry. Let me double check YouTube. See if anybody's hanging out there. Comments. Nope, no comments. 25 of you are watching. Great. It's good to know that people are joining live. Thank you. All right, so in-order traversal. Remember that an in-order traversal is left, then root, then right. So we're doing the root in between the left subtree, then the right subtree, the left subtree, then the root, then the right subtree. So our first process here is not A. We instead go to its left subtree and process the entire left subtree before processing A. Likewise, we recurse here and apply the same logic as before. Instead of processing B immediately, we go to its left subtree, left subtree. At this point, there is no left child, so we process L. There is no right child to L, so we end up not processing it. We come back up. Now, the tree rooted at G, we already did its left subtree, so we need to do G now. Remember, left, root, right. Now I go to its right subtree, but I don't process M yet because it has a left child. So it ends up being R, then M, sorry. At this point, I'm done with that subtree, and I return back up. I already did the entire left subtree of D, so I end up doing D. And then I go to its right subtree. I don't do H initially because I go down to its left subtree, but there is no left subtree. So no processing, come back up, then root. I did go left. It was empty, so no processing. And then I came back up, do the root. And then I went to the right subtree, N. This is H. I come back up to D, and I'm done. And then I return back up to B. I'm done with the left subtree entirely. So now I process B. And then I go to its right subtree. I don't process E initially until I've checked its left subtree, which is empty. And so I end up doing E next, just simply because it has no left child. I recurse. I don't process I process O first. And then I process I. And there's no right subtree, so there's nothing to process there. Return, return. At this point, I'm done with the entire left subtree rooted at A. So now A comes in. And you can see that everything up until this point is the left in the left subtree of A. A is right in the middle. And now I process the right subtree. There is no left subtree, so I go ahead and process C. Come down here. I need to process the left subtree, so P is next. There's no left child, there's no right child. There's no left child, then I process P, then there's no right child. Come back up. Now it's J, then Q. Come back up. Now I process F, and I process K at last. Right? So very, very different processing order by going with an in-order traversal. By the way, each one of these has their own applications that we'll talk about later on, which is why we cover all three. But as you might be thinking, only the order of the processing is different. The actual topology here, the actual path that you take throughout this thing is exactly the same. It's what's called a depth first search. Okay, and that's applicable to general graphs as well. And there is another one called breadth first search that we'll look at the very end here today. Okay. All right. Well, what about a post-order traversal? A post-order traversal is going to do a left, then a right, then the root. So as you can predict, the very last thing in this traversal is going to be A. I can write that down immediately at the end here, but I'm not going to do that. So we process left, right, root. So we go down to left, 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 left. There is no left, there is no right, so we end up processing L first. We come back up to G, but we don't process it yet. We need to take care of its right subtree first. When we go down to that right subtree, with M and R, we process the left, then the empty right subtree, then M. So R, then M. We come back up. We've already done the left subtree here at G. We've already done the right subtree. So finally, G happens. So you can look at it backwards here, that everything preceding this are all the descendants of G, L, R, and M. Right? We come back up here to D because we're done with the left subtree of D. But we don't process D right away. We go to the right subtree. We look at the left, it's empty. We look at the right, we have process N. And finally, we come back up here and process H. Okay? Now that we're done with the right subtree, we come back up, do D. We come back up. We don't do B yet. We do the right subtree first. We do the left subtree, then the right subtree before we do E. We do the left subtree, O, and there's no left subtree. We do the left subtree, right subtree, then O. Come back up. There is no right subtree, otherwise we would have done it. And we process I. Come back up. Now we process E because we've taken care of its empty left subtree, its right subtree, and so now we can process E. Come back up. Now we can process B. We come back up, but we don't process A. A is going to be the very last thing that we actually process. We come back down here and to do its right subtree first instead. Left subtree is empty, so we go to the right subtree. The left subtree, there is no left subtree, there is no right subtree, so we end up doing P next. Then Q, then J. So again, if you only have a 3-node tree, a pre-order traversal is going to be root, left, right. An in-order traversal is going to be left, root, right. A post-order traversal is going to be left, right, then root. Right? So that's why we've got P, Q, J over here. P, Q, and then J. Come back up. We process the right subtree next, K, because it has no children. Come back up, F. Come back up, C. Come back up, and finally A is the last thing to be processed. Okay? That is a post-order traversal. The last traversal that I want to show you is something a little bit different. It's called BFS, or breadth first search. And actually the difference between these two searches is going to be a callback yet again. We've now called back several times here to one of the mantras of this course, that a quote from Eric S. Raymond, that smart data structures and dumb code are a lot better than the other way around. The only difference is the type of data structure that you use when we actually implement this stuff. One of them you use a stack to keep track of your breadcrumbs, and the other one you use a queue. In BFS you use a queue. Now the idea here is with pre-order, post-order, and in-order traversal. They went as deep as in the tree as possible. We went as deep as we could over here, and then before we backtracked, and then went down a different path. Right? That's depth first search traversal. What I'm going to do with a breadth first search traversal is kind of like searching an area. If you know that you had an event here, or somebody was lost, a child was lost or something, then you search a perimeter of a radius 500 feet, right? And then you expand your search area into 1,000 feet, and you expand it more. You search around closer because it's likelier that they're closer to the epicenter than they are further away. You don't go off and go 10 miles that way and then return and then go 10 miles that way. You search around in a radial kind of arc. And that's the idea here. The radius, however, it's going to be more like this. Here's my initial radius. Here's my second radius. Here's my third radius, right? I'm starting at the root and searching in a radial manner for things at a particular depth, right? A BFS traversal, unfortunately, it's not going to look, it's not going to be all that interesting here, because the way that I wrote it was top to bottom, left to right. That's how you end up searching. You start at the top and you search the first row. Then you go to the next row and you search it left to right. So B, C. You go to the next row and you search it left to right. D, E, F. And since I wrote them top to bottom, left to right, it's just going to be your ABCs. Right? That's a breadth first search traversal. And you can achieve that just as easily with the data structures that we're going to present next time. Right? All right. Let me look at Piazza. No questions so far. So I will go ahead and save the implementation details of those for later, but I do want to talk just very, very briefly about how you might actually implement this stuff. So just like with a linked list, you are going to be linking a bunch of nodes together. So you probably want a node class if you were to do this in Java. And you would want to immediately parameterize it so that your nodes can hold students. They could hold doubles. They could hold strings. They could hold whatever you want. Whatever you want to put in this tree, you can put it there. Okay. So node T. What might a single node need? Well, you might need a left child and a right child. And if you really wanted to, that's sufficient. But what you probably want to do is eventually you'll probably want to know where you came from. Who's my parent, right? And so you probably want a parent as well. Each of these things is simply going to be another tree node. And I should have called it tree node instead. Tree node, because to distinguish it from a linked list node. But it'll be a tree node instead. You could also keep track of metadata. You could keep track of the item that's actually being stored at that node. You could keep track of its depth if you wanted to, but then you got to be careful then, because if you change the topology of your tree, when we say topology, we mean the structure of your tree. If you take this node and you swing it over and it becomes the new left child of this node over here, something like that, you cut up your tree and you rearrange stuff, you're changing the topology, you're changing the structure, then that could potentially change your depth. So maybe that's not something that you want to store. That looks pretty good, right? That's probably all you would need. So what does a binary tree implementation look like then? It'll also be parameterized. Do you keep track of every single tree node in an, you can, but then you're back at square one with an array-based list, right? Instead, what you want to do is you want to keep track of the single node, tree node T, called the root. And then over here, if you have the root, you can traverse to the left child of the root. Now that gives you a different node. You can traverse to the left, back to the root, which is its parent, or the left child or the right child. You can do whatever you want, and you can store stuff in it, and it's a very straightforward implementation, right? And we might end up using that. You'll definitely end up using that in one of your upcoming labs. Okay. All right. Last chance for any questions on the live Q&A. Doesn't look like there are any. So I'll go ahead and stop it there. And then when we come back next week, we'll look at the implementation details of these things. We'll look at some other. Then we'll start giving. Then what we'll do is we'll change a switch over and give it even more structure. The examples that we've shown so far, they just hold stuff. What we actually want to do is we want to exploit that structure in order to search for things. But to do that, we need to give it even more structure. We need to give each node not only contents, but we need to give it keys. A key will allow us to say, all right, well, I'm starting at the root here, and this is not the thing that I'm looking for. So where is the thing that I'm looking for? Is it in the left subtree or is it in the right subtree? The structure that we're going to give it is going to be, you're going to be able to make that determination. You're going to say, all right, well, the value that I'm searching for is larger than this key, so I'm going to go to the right subtree. Or the value that I'm searching for is less than this key, so I'm going to go to the left subtree. Is less than that key, so I'm going to go to the left subtree. Effectively, like binary search, it cuts out half of your search. It cuts out